Matrix presents overview of the RNS-APAL Demo application, a video tutorial. Hey RNS lovers! In this video tutorial, I cover the RNS-APAL Demo application, and I give you a little bit of insight in how this program works and what you can do with it. Alright, so if you've gotten this far, you'll see that when we run the RNS demo application, you should see basically a console menu, and this is where you can actually see some of the capabilities of the RNS-APAL software. So obviously over here we see some of the descriptions that these are basic features. And then here you've got some intermediate features, and then over here you've got some of the advanced features of RNS-APAL. So if we just start with the first one, increment an RNS number, we just simply type 1 because it's menu number 1. And when we hit enter, it'll ask us, this demo simply increments a starting RNS value. Enter a starting RNS value as a positive decimal integer. Well, oftentimes we just start with 0, and basically it prints it out, and you can see real quick what this looks like. So if I move up a little bit so I'm off the video inlay, right here we've got all of the moduluses listed along the top. So this is a special printout mode, and then down below we have the value of each RNS digit below that. And so this is kind of an interesting first introduction to the RNS-APAL system, so that each time we hit enter, you can see that the digits are increasing, and if we just keep doing that, notice the smallest digit modulus over here is 13. So when we finally got to decimal value 13, our 13 modulus is 0 as it should be, and if we continue off after that, you'll see that the 13 goes to 2, 3, 4, and so this is kind of an interesting way to see how each of the digits wrap around at a different point. And this represents a particular RNS value. So when we're tired of that, we can just come back and hit Q for quit, and it brings us back to the menu. Now obviously we can decrement an RNS number, we can add to us 2 RNS numbers, subtract 2 RNS numbers, and multiply 2 RNS numbers. So that's really pretty much there is to it on that. Let's go ahead and try to multiply 2 RNS numbers. I don't usually do these basic ones very often myself, but this one is asking now what's your first argument, and because the range of the RNS system is so large, we can just type any old number here, a large decimal number, and it'll go ahead and give us that decimal number. And then if we go ahead and add the second argument for the multiplication, it'll go ahead and multiply those together and give us what we're looking for. So when you see these things, really what's happening is you're getting a printout of the decimal value that you typed in, and it's always a good idea to look at the value that you typed in and then make sure that the RNS-APAL actually printed out what you thought you typed in, and that means you didn't do an overflow. And over here likewise you've got the second argument to the multiplication, and so you can see that was reflected correctly by RNS, and then you can notice that the actual raw RNS value is being displayed here. And so in this particular case, we've got a result, and the result here, you can check that with a calculator, is so forth. Okay? So if we hit Q, we can go ahead and exit. Now on some of the intermediate ones, convert RNS to mixed radix number, we can go ahead and try that. So we type 6, and then it'll give us an unsigned value to convert, because when we're doing mixed radix numbers, we're using unsigned numbers. And so again, I'll go ahead and just type some number, and when I hit return, it's first giving me a starting value. So again, it's nice to know that the string we typed in is actually the starting value. And then so every time we hit a key, we're going to go ahead and get basically this process. Okay, so what happened is, obviously the very first, mixed radix in this system always starts left to right in terms of the order of mixed radix conversion. And so you can see that there was a 50 before on the 128 modulus, and now the first step is to subtract that 50 from everything, and notice that the 128 modulus is now 0, and so therefore our first mixed radix digit is 50. And if we continue onward, we're going to do an inverse multiplication by the multiplicative inverse of 128 versus all the different modulus. And then we're going to move on to the next digit, which in this case was the 44 digit on the 81 modulus. And so this gives us our next mixed radix digit. And so if we continue to do this, you notice that this actually decomposes pretty quick. You can see now we're down to the value 6 here. And then one more subtraction of 6 gets us 0. And then it reports that, okay, we're done. And so when we're finally done, we can see that the mixed radix number in most significant digit first format is 6, 44, 50. So in this particular system, we were able to convert our number to the mixed radix equivalent. And notice that the mixed radix equivalent is being printed as a decimal number. Okay, so RNS-APAL has a lot of capability, but since there's a lot of number systems involved, you know, it may be that you want to print out things in hexadecimal format. It might be that you want to print things out in binary format. And then, of course, often we want to print out numbers in decimal format. Okay, so that was the convert RNS to mixed radix. And then we can reconvert mixed radix number back to RNS. We can do that demo, and that would be demo 7. And of course, you know, since we don't remember, well, let me see. Let me go see if I can type that same last number that we had here. And it'll go ahead and decompose this first. So just one keystroke, and it went through all those steps and gave me the 64450 mixed radix number as a quick first step. And then we're going to convert that back to RNS. And so it starts with the mixed radix number, the last digit converted, and adds it. And you can see that we just go right back in the reversed procedure to taking the mixed radix and turning it back to an RNS number. So one step by step, and you can see we finally got the final result here of 67,890. So that was that particular demo. Now these other demos here, I want to caution you about it. Convert RNS to binary and binary to RNS fractional. Some of these really need a little bit more work because the conversion is the most complicated part of RNS-APAL. And while conversion works pretty well in terms of using RNS-APAL, this particular demo doesn't do a very good job of showing what's going on inside RNS-APAL. So probably skip over 9 and A because, well, not A, that's compared to RNS digits, but the convert RNS to binary and binary to RNS fractional, those two particular conversions aren't really representative of how the RNS-APAL works. It's one of the things that it's on the to-do list to fix those up. Obviously, you can compare two RNS numbers. That's always a useful one. So if I hit A, you know, let's compare 1, 2, 3, 4, 5, 6 with the number 1, 2, 3, 4, 5, 7. Obviously, the second number is larger. And basically, the way it's going to do it is just going to use mixed radix conversion. And it's going to do it one by one. And so it subtracted 64 from the top one, but it subtracted 65 from the bottom one. And then press a key. And so it's showing you how this is actually compared least significant digit first. And since 64 is less than 65, A is less than B at this point of the comparison. And then as you continue to press a key, you go ahead and go through each one of the digits. And in this particular case, the A is always going to be less than B through each step here because of the numbers I've chosen. So the comparison is complete and A is less than B. Oftentimes you'll find out when you compare two numbers that doesn't actually work out that way, because remember, when you're comparing mixed radix numbers, you're comparing least significant digit first. And so the software has to track which number is bigger than the other number as you're comparing digits. And it's only until you really look at the most significant digit, and that's the last digit that's actually checked, do you really know the answer. So when you play with the comparison, you'll find out that the A is less than B and B is less than A, and that might just flip back and forth as the comparison is being made until the entire comparison is done, in which case the answer should be right. Okay, so keep that in mind about comparison, because comparison in RNS is tricky, and if you're using mixed radius conversion, we're comparing least significant digit first, and it isn't until we get to the most significant digit that we really know what the answer is. And there are a couple of caveats there real quick. I'll just mention that sometimes when you're doing mixed radius conversion, a very, very large number will terminate and go to 0 before another one. I can show you that. That's a pretty easy thing to show. So if we go back and type B for compare two RNS, or go back and do A for comparing two RNS numbers, if I make one of the numbers very large and I make the other number very small, what'll happen is you just keep comparing, and as you step through here, you'll notice that B now finally went to 0 here, whereas A is still got quite a bit more to decompose before before mixed radix brings that to 0. And so notice that the comparison says A is greater than B by early termination, and the comparison is correct in that case. So shows you some of the style on what's going on. It's kind of interesting because mixed radix conversion may take longer on some numbers than it is on the other numbers, and this gives you some insight into the algorithm for comparison. Okay, moving on, we've got divide two RNS integers. This is an advanced feature, so it's one of my more interesting achievements here in the software. But here we can just type a number, let's say, well, let's make an easy one for us, 1,000. And then you could go ahead and what's the divisor? Let's say we want to divide by 100. And you can see that when this types out, the result is 10, the remainder is 0, and it's actually giving the result here, and this is actually the value of 10 in RNS. And a couple of things are presented on this particular demo. The division steps are actually shown, and you can look into the manual about what the meaning of these steps are, but essentially what it is that the numerator was divided by 4, and then it was divided by 25. And notice these are powers of the existing modulus. And then some of this stuff also means maybe there were a base extension involving 3 steps. And the star, I believe, is a comparison. And so then it does it again. So this is the next iteration through the division. And again, it'll divide by the same numbers because those divisions are controlled by the divisor, which doesn't change. So these are the steps of the divisor, and you can go back to the RNS-APAL manual and it gives you a better explanation of what these little codes are, so you can actually see the steps of the division. Down here, because division is so critical and we're always trying to optimize division, we actually give a count on what we think the clocks would be if this was implemented in hardware, in a hypothetical situation. And so it kind of gives you some kind of idea how long this took. And then it comes back and says, well, do you want to do another one? And because this is an integer division, I can type in a very, very long number as long as I don't exceed the range. And again, if we hit return, notice that this number that printed back out is exactly the same number that we typed in. So this is telling us that we're still in the range of our RNS number system. And then I can just go ahead and give another big number that is maybe about half the string length here. And so this is a much more difficult comparison. But when we hit return, we can see that the comparison, the divide, had a lot more steps in this particular case. And interestingly, the number of steps is actually data dependent. So it really depends on how the two numbers really interact with one another. But in this particular case, we got a result, and this was the final result, and this was the remainder, and prints out. And as you can see, it took many, many more clocks to actually divide these two numbers. And we can try it again, and sometimes the results come out different. So in this case, notice that it did accept my number. And then if we just go ahead and give it some more numbers, notice that this one is much less. So these two particular numbers took less number of steps to divide out. Here's your result. These are the remainders. And of course, a lot less clocks. And so one of the things that I'm trying to do in terms of the algorithm design for division is to tame this algorithm a little bit more and make it a little bit more predictable, and obviously lessen the number of clocks that are required to divide two numbers. But on the other hand, you can see that these divisions are quite large, and they're actually larger than typical divide that might be done in as a native format. For example, in C, these are much larger numbers, and so you know, the algorithm still performs and still completes the job. So if we hit Q to quit, we go back, and the next one is fractional multiplication. So if we hit D, notice it gives you an example format of what it expects, and you can see that this one is signed. So we could say 234.567 and multiply that by, say, 100.099. And here we've got an answer here, and of course it's a negative answer, and 0.922133. If we were to get a calculator, you know, you could get a calculator to test this out and see if this is something that makes sense, but you know, I won't do that here. Those are some of the things that you can do yourself. And you know, interestingly to say is that even though we're showing the values in decimal, and it looks like we're doing a decimal calculation, because this is a fractional format, you have to remember that we're in a different number system with a different range in a different space. And so, yes, you're not always going to get exactly the same number as decimal calculation, because these aren't decimal calculations. And in fact, when you type a decimal number in, you're just getting the closest approximation to that decimal number that's available in the RNS number system. So that can be tricky to understand, but you have to just keep in mind that when you're dealing with a different number system, you are in a different space. It's the same thing with binary. If I was to tell you to calculate a number, say 10.2, which is 10 and 1/5, many of you know that you can't represent 1/5 exactly in binary, and so you can't expect to multiply exactly 1/5 by any other number in the binary system. You're never going to get an exact result, because the binary number system never actually represents 1/5 exactly. So these are the types of things that actually happen in any number system, and in the RNS number system. The RNS number system, when we're doing fractions, has a different properties. And it turns out that we can be very, very accurate, because depending on the number of fractional digits we choose, which is I'll show later when we go over main again, we can choose how many fractional digits, and because we have different modulus in the fractional space, we can actually do many, many more fractions exactly than binary or decimal in the general case. So that's the example on the fractional multiplication. All right, moving on, we've got a square root, a fractional square root example. That's E. So if I type E, we can come in, and let's say you want to get the square root of 2, so we can just type in 2. You can also type in 2.0, and there you go. So in this particular case, this is performing square root using Newton's method, and it's taking all the basic arithmetic capability of RNS, such as multiplying by fractions and being able to divide integers, and it's taking those operations and using Newton's method and actually calculating the square root in the RNS domain. Now notice that it says 1.41421356 blah blah blah, and it has a little plus sign. The little plus sign means that there was a little bit more to the value than what would be displayable using that many digits in decimal, but we don't want to expand out the decimal much farther, because that's an incorrect representation really of what's going on inside the RNS number. So a lot of thought went into how these things are being plotted out and printed out between different number systems. Notice also you have a V. You might have been wondering, what the heck is the V going on in a lot of these numbers? Well, V means that the signs are valid, because again, I won't go into too much detail, but we do two different ways of tracking sign in RNS. One is using the method of complements, which is the most important method, because that allows the calculation to carry the sign of the result automatically. But we also carry sign bits, and the reason why we carry sign bits is that at times, once we store the sign bit, it's easier to look up the sign of the value than to look at the number and try to compute the sign of the number. So it's a technique that RNS-APAL adopts, and that is that tracking signs uses two different methods. One is the method of complements, which is the more important method. The other method is to track sign bits if it can. So that would be a sign magnitude notation approach. Okay, so V just simply means that the sign bit is in agreement with the complement. The complement always being essentially the correct answer, because sign bits don't always survive a calculation, and we can't always know what the sign bit's going to be unless we actually compute the sign of the number. But in the case of printing out always computes the sign of the number, and it checks it against the sign bit that's stored there, and if they agree, that's going to say V for valid. And a lot more about sign bits is in the manual, and I certainly welcome you to study that a little bit. Calculating signs and tracking sign in RNS is, a little complex, but it's not difficult once you understand the methodology that was used here. And again, the method of complements is the chief method, and sign bits is just kind of an extra feature, basically. And it turns out that tracking the sign bit is one very good way to check overflow, and it's another good way to validate your results. So it turned out that tracking sign bits as a sign magnitude notation really had an unintended feature, and that is to really let you know whether your calculation is correct or not. So if you see the V being an E or an I should say, that means invalid, and then you know that there was a problem in your calculation. So it's an interesting result of sign bits. And the last thing here, we went ahead and squared the RNS number, and we get back the 2.0. In this particular case, the square root, when we squared the square root, we got exactly back to where we want. That's a nice result. It doesn't always work out that way because of the way that arithmetic works in these number systems. And that's the case with binary and decimal as well. If you take decimal square root to so many places and then you square that square root, oftentimes you'll get, just a little bit less than the number you started with. For example, if you did 2 and you did a square root of 2 with a certain number of places, when you multiplied them together, the square root of 2, you might get 1.999999999, something very, very, very close to 2. And the same thing happens here on the RNS system too. But don't confuse yourself. The entire calculation is done in the RNS format. We're just printing the results because us humans, it's easier for us to actually see a decimal number. So don't think that what's happening here is that we're doing these calculations in decimal and just somehow printing the RNS, for fun. That's not what's going on at all. We're actually doing the calculation in the RNS system, and then there's a print routine that does the conversion from any given RNS representation back to decimal so that we can see what's going on. So this particular square root and all the other calculations in the RNS-APAL are being done in the RNS number system. So let's try another example. If we took, for example, 100. 100 is a well-known number. So if we took that, in this particular case, you can see that, we got the square root of 10, and when we multiplied 10 by 10, we got back to 100. You'll notice that the first digits are all 0 in many of these cases, and these are the fractional digits, and because you're dealing with whole numbers here, all the fractional digits are 0, just like they would be in decimal or binary. If you had a decimal or binary system that had fractional digits, but you had a whole number, then all those fractional digits are 0, right? Same case with RNS, so it's kind of a little bit of a giveaway there. Let's try a different one. 600.25 is a good one. That's a fraction, a square of some fraction, so that's why I have it as an example there. So we'll go ahead and pump that one out. And once again, you can see some of the interesting things about the square root. The 600.25 is not quite a whole number, but it is something that can be easily represented by this particular system, and that's why you get a lot of zeros, but the 128 is not 0. And notice that the 0.25 is what? 1/4. And so you start to see some correlation there if you really notice these things a little bit closely. In this case, I didn't get what I wanted, so let's go ahead and just try any old number. So I've got a much bigger number here, and I'm probably not expecting to get an exact square root on this number because of the precision of the system. So let's go ahead and try that. And sometimes it takes a little bit of time for the number crunching to get done, but here, let's see, did we get that exact? No, we didn't. So we got a square root here, but when we actually multiplied them together, we've got very close, 2, 3, 4, 5, 6, 2, 3, 4, and then it differs right here. So the last 4 digits, 4926, should have been 5,000 right up here. So we were off by that much. And again, this is a consequence of finite precision arithmetic. And this is the same type of thing you're going to get in binary. It's the same thing you're going to get in decimal. But it does basically demonstrate the square root capability in this number system. And so it's very interesting to play with this. We'll do one more. Let's say we wanted to do the square root of 11. So here's a case I like that I think is very representative of what I've been talking about. We started with 11. We got a square root that goes to some certain amount of precision, and then when we multiply the square root by itself, we end up getting a value very close to 11, but not quite there. So when we print that value out in decimal, notice that we also get a value very close to 11. So the decimal equivalent is 0.99999. I don't know how many nines are here, but there's a lot. And if you took a closer look at it, you notice that the original 11 had zeros because it's a whole number in the fractional digits. But here we're off by a little bit. So had this gotten, say, 4 or 5 more units ahead, then we would have gotten an exact number. So giving you some insight into basically how fractions work in the RNS domain. Okay, so we'll quit out of that. We'll move on to inverse by integer divide. So oftentimes, fractional division by integer divide. So there's more than one way to skin a cat, obviously, in arithmetic. And for this particular one, when we do that, we're actually going to be dividing fractions. Remember, in C, we were dividing 2 RNS integers. Here, we're going to be dividing 2 RNS fractions. So let's say we take 100.5, and we want to divide that by 0.25. And as you can see, the result is as expected. It's 402. So in this particular case, we got a nice perfect result because we have a very even division. And when you do fractional division using integer division as what is actually doing the division, and again, the RNS-APAL manual touches a little bit on that formula, you get the closest result that you can get, just like you would get in a calculator for this number system. So for example, if we take a bigger number, for example, just any old number, and I go ahead and divide that by some other number. Oops, I'm gonna make sure you have numbers here. Then you get a value, and it's very, very close. And notice these are the values I typed in, and then of course this is the value that you get as a result of that fractional division. And this is something that you could check on the calculator and, at least in terms of decimal representation, figure out, well, how close was that. But once again, I always caution everybody, you got to remember what's really going on here. These are decimal numbers that we type in because we're humans, and then the RNS number that's representing this decimal number is getting as close to that decimal number as it can. It's not exact. And so when you're starting with numbers, you're not really starting with decimal numbers. You're starting with approximations to those decimal numbers. Then when we do the division using this particular algorithm gets as close as that number system can be. But then when it prints it back out to decimal so that us humans can read it, there's a little bit of error there. So you have to kind of understand that when you're converting between different number systems, you are going to incur conversion errors. But this particular routine for the actual fractional division is as close as the number system allows. So again, I'll quit out of that, and you might say, well, what do you really mean by as close as it can be? Well, you have another way to do a fractional divide, and that is and that is the fractional divide using the Goldschmidt algorithm. In this particular case, we're not using integer divide to actually perform the division of the fractional numbers. We're using Goldschmidt's algorithm, and that has more of an error. So if we type in 1200.25, for example, and we want to, let's see, got a little bit off here. Let's see if I can reset this. We're going to fractional divide by molt. So we're going to stick I. Okay, here we go. So if we went ahead and said 600.25 and we wanted to divide this by 0.25, notice that we're not getting a perfect whole number here anymore. We're getting a very, very close number, and notice the end has a little bit of a rounding error, so to speak. So this is what happens when you perform another algorithm and you're trying to divide fractions in RNS using another algorithm. In this case, it's the Goldschmidt algorithm. What's the advantage of doing an algorithm like this? Well, it's only taking fractional multiplication. And in order to pull off fractional division using fractional multiplication, we need to be able to scale. So the significance of this algorithm is really being able to do the scaling of the RNS number. And so that was a pretty big achievement, really, to figure that out. And there's some information here in this patent, for example, if you wanted to see, you know, what my original ideas were. And then, of course, you can look at the source code and try to figure. This is one of the more complicated ones here. So trying to do scaling of fractional numbers, because remember, when you're doing Goldschmidt routine, you've got to scale the divisor to a value less than 1. Otherwise, it doesn't work. So and then, of course, because of the numerical precision, if you really skew the numbers quite a bit, and for example, put in a smaller number, then you can expect to get more rounding errors, mainly because the Goldschmidt routine itself is not capable of creating as accurate a result, and that's purely because of the numerics, the fixed precision. But you can also underflow or overflow calculations using this as well, so that's some danger there. I've recently fixed their bug in this particular algorithm because it was one of the more trickier algorithms to try to get done in the RNS domain. So I'll go ahead and quit out of this. And I did jump over fractional inverse by integer divide, so we can do inverses. So if I hit H, you know, an inverse of 2 would be 0.5. And whenever you do any calculation using integer division, RNS integer division is kind of slow, but you do get a very, very accurate result, because integer division is maintaining the full accuracy of the numerics of the system. So unlike something like Goldschmidt algorithm, applying pure integer division to your calculations is going to give you the best result possible. So let me try another one. Let's see if I can get creative. I'm not sure I can get creative. 600.25, and if we invert this, then we're getting this kind of number here. Okay, and again, I think what if I typed this number back in and did an invert? Well, if I typed that back in, 001665972 you see this isn't exactly the number that was represented by RNS, because you can see there's a little plus sign here. So by me typing this number back in, I'm not even going to get the same number back, RNS number back, because it's not quite as accurate. And notice when I re-invert it, I get something very close to 600.25, but there's some error here. And that error is mainly attributable to the fact that I was not able to actually, using the decimal number system, I was not able to re-enter the exact inverse. And in fact, if you look at it, this is the value I typed in. Let's see, this is, where's the value I typed in? This is the value I typed in, and it said 106, and this is the value that was calculated in the previous step, which is 120. So you can see we're off a couple of clicks. I call them clicks. They're a few units in this number system. And so it's close, but it's not exact. And then, of course, the ramifications of not coming in exact is you're going to get some error offset there. Okay, so keep in mind that the RNS number system is a whole different number system. Now, if you were to do all your calculations on RNS, you're going to get a very, very accurate result. And the more that you stay away from converting back and forth between, say, decimal or binary and RNS, the more accurate your result's going to be. All right, so I think the last one here is I did a product summation, and I'm not going to go too much on that product summation. You can go through that, but basically product summations is the power of RNS, because this is really the area where we're going to get the most bang for the buck in terms of moving into this number system. So for very large product summations, like in neural networks and machine learning, I'm hoping to apply RNS because we can get a carry-free product summation, and we can get a very accurate result. And then we can do, because we're in another number system, there's other benefits to that number system. And one of the latest ones that I came up with lately was the error correction of general purpose arithmetic. And what I mean by general purpose arithmetic is I really mean signed arithmetic using the method of complements. So if we can do error detection and error correction of massive product summations that were fully signed and fixed point fractions, then that's a new feature that's available to us in this number system that wasn't available in binary or decimal. So, this is a very interesting product, and many hours went into building this code, and I just wanted to demonstrate this RNS demo menu for you. And in the next videos, because I went a little long here, we'll talk a little bit about how to use the RNS-APAL software for yourself. And there are basically some styles of programming that is the best to use on this system, and basically I hope to show you that it's not as bad as it looks, but you do have to know a little bit about C++ and how to allocate class objects. Okay, so I hope that at least wraps up the introduction to the RNS-APAL software, and I appreciate your time, and I hope that you find the RNS-APAL software an interesting tool that you can use, and you can use for your own development and analysis of RNS number systems. Thank you. This concludes the video tutorial on the RNS-APAL demo program. In the next upcoming tutorial, I'll show you how to actually write your own programs using the RNS-APAL library. Until then, take care.